Now that we've learned how to draw free body diagrams of bodies of interest, and we know how to deal with support forces, and also we know how and what equations of equilibrium we have to write, so let's look at a couple of examples in order to see how to apply all these concepts to practical questions. In example number 1, we have a horizontal beam. I'm drawing just a portion of it, so these squiggly lines at the ends are like just indicating that the beam is interrupted, so the beam is much longer. It has two horizontal plates at the top and the bottom called flanges, and in between these flanges there's a slider, the one that I drew in blue, that is making contact with the flanges at points A and B, and at the left end of the slider there's a device with a hook which can support a mass of 300 kilograms. So that would be point C on the slider. So the whole device can act as a crane, as a lifting device. Now, a few dimensions in the horizontal directions. Between A and C there are 400 millimeters and 600 millimeters between A and B. What you need to calculate now is the reaction forces at points A and B. So the first thing that you have to determine is what would be the rigid body that you have to consider to isolate. Well, you need to see those two reaction forces which are internal to the system, so you have to cut through their interface. So you have to cut at A and you have to cut at B, and you also will cut at C, and hence you can totally take out the slider from the system. Imagine that you cut with the scissors along the dashed line. So once you free up the slider, your body in question, let's redraw it again and replace the reaction forces at A and B with AY and BY. These are forces normal to the flanges of the beam, and assuming that the flanges are smooth, so there's no friction, hence the slider can slide freely horizontally, then we will only have a normal force, and in each case, and these forces will be obviously vertical. Of course, the weight W at point C and the required dimensions, and this would be the free body diagram of the slider, for which we need now to analyze equilibrium. But first of all, let's convert the mass into a force. So W will be equal to 2.943 kilonewtons after I change the units from newtons to kilonewtons. And now let's write the three equations of equilibrium. The first equation, sum of Fx equals 0. It's the identical equation because we don't have any components along the x direction, any force components along x. Sum of Fy, the second equation, equals 0, is Ay plus By minus the weight equals 0. But, oops, we have two unknowns here, Ay and By, so we can't do really anything. But we can write the third equation by summing the moments about, say, point A. And by doing so, we will eliminate Ay, because Ay goes through point A. So that's the big benefit of moment equations. We have eliminated one of the two unknowns, and the resulting equation will contain only one unknown, and that would be By. As I said, moment equations are your best friend. So from the third equation, we can quickly solve for By, which will result as negative 1.962 kilonewtons, meaning that the original direction that we assumed, and we should always assume the positive direction of the forces, so going up, but meaning that that direction was wrong. This is the meaning of the negative sign. So therefore, in this case, By will go downwards. Now, once we have solved for that, we can plug in the value of By in the second equation with its corresponding sign. And from here we can solve from Ay, which we will get for Ay a positive number, so therefore the direction of Ay going upwards was correct. Our initial assumption was correct. So as you can see, when we write these reaction forces, we assume a direction, which I suggest to always use the positive direction of these forces or moments. And then the final sign of the result will indicate whether our direction was correct or it was incorrect. So if it's a negative sign, it means our initial assumption was wrong and the direction of that reaction force is opposite. Now let's continue with a second example, a more interesting example, in which there is a mast, vertical mast, fixed at the ground level and also connected by two cables to a ring. Let's put some letters. So cable AB and cable DB, they both connect to the mast and the ring at B, and then there's a third cable from the ring at B to the ground at C. The height of the mast is 10 meters and some angles of the cables are as given, as shown. Cable BC is fitted with a turnbuckle, and the turnbuckle is a device that can stretch the cable and hence input a tension force in the cable, and that force will be equal in this case, the force in member BC, in cable BC will be equal in this case to 1.6 kilonewtons tension. The question asks to determine the moment at the base of the mast AD. So let's call that moment MD, so the moment at D. So in order to solve for MD, let's see what we need to look at here. Of course, we have to cut a D because we need to find that moment internally, a D. And in order to remove the pole from the system, we also have to cut cable AB and cable DB. So we've done 3 cuts. And all these 3 cuts in the free body diagram of the mast that I'm going to draw now, we have to replace what we removed by cutting in 3 locations. We have to replace what we removed with internal forces, and that would be the tension force in cable AB, making an angle of 30 degrees with the pole, the tension force in cable BD, and this force makes an angle of 45 degrees with the horizontal, and the internal forces at the fixed support at D, dx, dy, and md. As you can see, I'm showing all these 3 forces with their positive directions. It's just an assumption. If the result will be negative in the end, that means that my original assumption was wrong. So there's no problem. Just select these forces with their positive direction, and in the end your sign of the result will tell you if you are correct or no. In order to solve for MD, the easiest equation to write is sum of the moments at D, because that will get rid us of the other 2 unknowns, dx, dy, which we don't have to calculate. They're not required in the question. So if we write this equation, we end up again with an equation in having 2 unknowns. So we need to figure out how to solve for FAB, because otherwise we will not be able to solve for MD. So FAB also acts at particle at B. So if we now isolate the particle at B by cutting the 3 cables that surround the particle, we can then draw the forces in those 3 cables on a free body diagram of particle B. So this would be the force in member BC, which we know equals to 1.6 kilonewtons in magnitude. And this one here would be the force in cable AB, which we need to solve for. And the third one is the force in cable BD, all of them tension forces because they're cables. And let's also write these angles. that these cables make with the horizontal and the vertical respectively. And now all we have to do, once the free body diagram of the ring is completed, write the equations of equilibrium for particles. If you remember, particles can only translate in two directions, so they have 2 degrees of freedom. And hence we will write two equations of equilibrium, summation of forces along x, which is the one I'm writing right now. I'm expressing, as you can see, everything in terms of cosines, and you will see in a second why I do that. Let's simplify this expression a little. So this equals to 1.386, and let's call this equation equation number 1. And the second equation, summation of forces along y in the vertical direction, again expressed in terms of cosines. You will see that if we were to add these two equations later, because they're expressed in terms of cosines, both some of these terms will cancel out, and we'll end up with a very simple relationship from which we can solve quickly for the forcing cable AB. So let's simplify this expression. This equals to 0.8, and this will be the second equation. And as I mentioned, if we add these two equations together, we will end up with 1.366 FAB equals to 2.186. And from here we can solve for FAB as being also 1.6 kilonewton meters. Note how I use the number of significant figures. Number starting with 1 requires 4 significant figures. And then all we have to do is plug in this number into the equation of moment that we had developed earlier. And from here we can solve for the magnitude of the moment at D, which is a positive 8 kilonewton meters. So hence our original positive direction rotating counterclockwise of the moment was correct. So again, this is the way to solve a question like this, equilibrium in 2D. This question required 2 steps. And again, remember, when you assume directions of the unknowns, it's just a guess, and the sign of the result will indicate you if you are correct or not. Thank you very much for watching this video, and I will see you at the next lecture.